In a previous video, we found the Lagrangian for this situation of the disk rolling down an inclined plane. And we did that by finding the Lagrangian, putting it into the Euler-Lagrange formula, and then using this equation of constraint to eliminate one of the variables. And then we were left with this differential equation of motion. And in this video, I want to actually solve that differential equation so we can just have the function x of t rolling down this plane. So we can plug in a value of t and we'll know where exactly this thing is. So here's the differential equation we're trying to solve. As differential equations go, it's not super complicated, right? It's just has one term with x in it, that's a derivative, no other x terms. So we can actually do this just by integrating. So the first thing I'll do is I'll solve this for x double dot, and I'll skip some of the algebra steps. So x equals 2g sine of alpha over 3, right? We would add this to both sides. We would divide by the 3 halves m. These m's would cancel. And here we go. We have x double dot equals all this stuff. So now since we have a derivative of x, or a second derivative of x with respect to time, we can integrate this with respect to time. So I'll integrate, then I'll squeeze a dt in here. Sorry, it's a little cramped. But anyway, and then we'll integrate both sides, dt. So this side, this is the second derivative with respect to time of x. So if we take the time, or if we integrate with respect to time, we'll just get the first derivative, x with one dot above it. First derivative with respect to time. And for the other side of the equation, none of this stuff depends on time. Gravity's not changing with time. The angle of the alpha is the angle of this inclined plane. It's not changing with time. It's just sitting still. So all of this is just a constant. So we can bring it outside of the integral. And then the integral of dt is just t. So we'll have 2g sine alpha divided by 3 times t to the first power. And then since this is an indefinite integral, we need to add a constant, right? So what does this constant mean? We know that this constant is going to have the same units as the other terms in the equation, and it turns out that this is a time derivative of position, so this is going to be a speed, and this will end up being the initial speed of this disk rolling down the plane. So initial speed, right? And we don't know what that is, but in a specific situation, we might know what that is, and then we can just put it in here, and this is a nice general equation for the speed of this thing rolling down the plane. But the main thing we're looking for is just x of t, not time derivatives of x of t, but x of t. And this is a function of t as well, right? It depends on time. But if we want to find just x of t, all we have to do is integrate again. So I'll integrate here. I should really leave more room for my dt's that I'm going to put in, but I'm integrating this with respect to time, and since this is the first derivative, integrating it just gets us back to the original function. And then we need to integrate each of these terms. So this is still a constant with respect to time. When we integrate the t to the first power, we'll get t squared over 2, and then the 2 in the denominator will cancel this 2. So I'll write g sine alpha divided by 3 times t squared. All right. Now we can integrate this constant term, this other constant term. So plus, since this is a constant, we just integrate. Well, I should actually write my integral here, dt. And we're doing this whole thing. Right, so we're integrating these, and we integrate term by term. So this is a constant, so it'll come outside of the integral, and then we'll just get a first power of t. And then since this is also a second derivative of, or excuse me, this is also an indefinite integral, we need to add another constant, and I'll just call it d. We could call this c1 and this c2. There are different ways people like to name constants, but I'm just going to call it d. And this constant, the physical significance of this constant, is the fact that this disk can start in different places. We can call t0 different things depending on where we want this disk to be when it starts out. So the c is the initial velocity of this disk. The d is the initial position of this disk. So we're already finished. We have x as a function of t. We can see that it looks like the function of a parabola, or it's a quadratic function. And one thing you might notice is that this looks a lot like one of the kinematic equations, right? This is x as a function of t depends on the initial position, and then the initial velocity times time, and then half the acceleration times time squared. And this is actually, this term right here, this constant, is the constant acceleration of this disk rolling down the plane. It's not just g because it has to interact with the plane, and there's this friction, and it has its rotational energy and all of that. So it's not the same as just g, but it's still a constant acceleration term. And anytime there's a constant acceleration problem, you'll end up with an equation like this. And just to cap things off, I'll write initial position. Initial position. Initial position. Here we go.